In this lesson, we're going to start to analyze some of the components that establish our network infrastructure. These would be the core pieces of our network that make the network actually function. So let's dive into this and see where it takes us. In this diagram, what we see are a handful of different definitions that are going to be critical for our continued discussion and study of networking infrastructure. First, what we see in the middle here is something called a router. Now, this is a layer 3 device that operates at the network layer of the OSI model, and basically this is the guy that connects our segments together. As you can see, we have a segment that spans off to the left of the router, a segment that spans off to the right of the router, and another segment extends upward from the router in this diagram. So the router and the one interface on the router that connects to each segment defines the segment. So the segment on the left is the network interface on the router, and then all the nodes on that left segment that are attached together through hubs and the bridge that's there in the middle. That is the mechanical, physical construction that is a segment. Now, the hubs are connection devices. They typically aren't used today. However, they were part of the original networking infrastructure. Today, these have all been replaced by switches, but we'll be covering those details shortly. They are a centralized concentrator, and we establish a physical star on the network topology from that hub. So we have one cable that connects directly from the hub out to each discrete node. So that's one cable. Separate cable for a second node, third cable for a third hub, etc. And as a result, these devices all now live on this same segment. Now, the segment that we see here to the left of the router also includes something called a bridge. Now, the bridge is a layer 2 device, and the layer 2 device finally has some intelligence and does some filtering based on MAC address. The bridge was an optional component on a segment, wasn't really required. However, if the segment got too populated, too busy with nodes and traffic from those nodes, then we would have to break that segment in half by placing a bridge in the middle. And this would reduce the amount of traffic on each half of the segment now. Now, with the bridge in place, this still is one contiguous segment. So from the network interface card on the router, through the first hub on the left, through the bridge, through the second hub on the left, and to all the nodes that are attached to those two hubs, this is one segment, and it is a physical construct. Now, we can assign some IP address space. IP is a layer 3 protocol, and it is a logical assignment of IP address to each and every one of these nodes. In this case, in this example, we have the IP subnet of 192.168.10.0 with a /24 mask. Now that /24 mask is its subnet mask, and it defines a subnet mask that equates in dotted decimal form to a 255.255.255.0. If I wanted to, I could assign a second subnet to this same segment. So I would take, let's say, 10 of the nodes on this segment, and I might give them a 192.168.200.0/24 subnet address. And this would be a single physical segment, but could contain one or more, as I just described, logical subnets. The subnet, again, is that logical assignment of the IP address space to the nodes that occupy this segment. All right, so there's some key definitions there. Now, the next thing we need to understand are the couple of terms down towards the bottom of that particular segment, and that's the difference between a broadcast domain and a collision domain. Now, as you recall, I described an overpopulated segment with too many nodes and too much traffic on the segment. And we started getting broadcast storms or collision storms, and this became a very inefficient segment as the population and the traffic on this segment increased. And if it got to the point that efficiency was so bad, the users were starting to complain performance was bad, our solution was to reduce the number of nodes on each half of the segment and isolate these two halves, separate them with this device in the middle called the bridge. Now, the bridge is a layer 2 device, does filtering based on MAC address. And we'll be studying a little bit more about the bridge in a minute, but basically, a node on the left-hand side of the bridge might send out a frame onto the segment. However, the bridge would look at the MAC address, the destination MAC address, and would know whether the destination is on the left side of the bridge or the right side of the bridge, and would only forward that frame to the right side of the bridge if the destination was on that side. If the destination was on the left-hand side of the bridge would simply discard the frame and would never populate the right-hand half of the segment with that transmission. So we reduced the amount of traffic on each of those two halves. Now, this broke the segment up into two different collision domains because there is no way that a node on the left could ever transmit a frame that would directly collide with a frame transmitted on the right of the bridge on that same segment. Because the only way a frame from the left would ever make it to the right-hand side of the bridge is if the bridge captured the frame, stored it, and then logically, if it concluded it needed to be transmitted to the right half of the segment, it would then transmit the frame to the right half of the segment. So the left-hand node never directly communicated with the right-hand node. It only ever communicated through that intermediary bridge. If a collision was to occur from this transmission, it would be the bridge that collided with the frame on the right-hand half of the segment. So we took one segment and broke it into two half segments called two different collision domains. Now, this tended to reduce the amount of traffic on each of the two halves of this one segment. The next component we would need to talk about is this broadcast domain component. And in this regard, when a node on the left would transmit a broadcast to the layer 2 broadcast address, which is all Fs. If you recall from an earlier lesson, a broadcast address at the layer 2 is all ones, which translates in hexadecimal to all Fs. Well, the broadcast at layer 2 says send this frame to all MAC addresses on the segment. Well, the bridge says all MAC addresses. Well, that includes all the guys on the left side and all the MAC addresses on the right side of the bridge. So a broadcast sent on either half would be transmitted eventually through the bridge to the other half. So all the nodes on this segment, including that one interface on the router, would receive that broadcast, no matter what node it was transmitted from on the segment. So we still had one contiguous segment, one contiguous broadcast domain, but we broke the segment up into two different collision domains. And then on top of this segment, we could, through logical controls, through the IP address space, we could assign one or more logical IP subnets. We'll take a break here and we'll pick up with this definition or description of the networking infrastructure, segments, subnets, and other components relative to the networking infrastructure. Continuing with our definitions here, let's look at the segment. As we said from the preceding lesson, the physical media, the connectors, the nodes, and even the network interface card on the router that is the default gateway for that segment, this defines the segment. So the router is the boundary of the segment. It will typically have one IP subnet, which is a logical assignment of the IP address space, because I could choose 192.168.10.0/24, or I could use 10.10.10.0/24. It doesn't matter to the network which of those number schemes I choose or which of those IP address spaces I choose. I can just logically choose them from the private address space and assign them to the nodes on the segment. I could also bind a second IP subnet address space to a series of nodes on that network, and then I would have multiple subnets on a single segment. So the subnet, as we said, is a logical address assignment applied to the nodes on a segment. And the example here is a 192.168.10.0 with a /24 mask, which equates to a 255.255.255.0 subnet mask. And again, you can assign multiple IP subnets to different nodes on the same single segment. As long as your router understands what's going on, as long as your router has both IP subnets associated, we can route from one of the subnets to the other subnet on the same segment. We talked about the collision domain. A collision domain is bounded by a layer 2 device or a layer 3 device. So the layer 2 device is the bridge, the switch, and the layer 3 device is a router. Now what this says is if a node transmits a frame onto the media, which is the segment, that transmission, that frame will transmit all the way up to one of these 3 devices, the bridge, the switch, or the router. It will impact the interface on the bridge, the switch, or the router that the same transmitting node is attached to. However, it will not commute that frame immediately to adjacent connected segments or other parts of the segments. These devices do what's called store and forward in most cases, and the bridge, for example, would receive the frame, store it in memory, analyze the MAC address, specifically the destination MAC address, compare it to his MAC address table that he has stored in memory, and then make a forwarding decision whether or not to transmit this frame to the next piece of the segment or whether he can discard it. It depends on where the destination is. The same with a switch. Now the router would look at layer 3 information before making that forwarding decision. And so it also would be that store and forward device that would never allow a frame on the left-hand side to be transmitted automatically to the right-hand side. It actually is the router that would be transmitting that frame to the right-hand side. And as a result, it would be the router on the right-hand side that would be the source of a collision if such a collision were to occur. So these 3 devices, the bridge, the switch, or the router, are all devices that establish the boundary of a collision domain. But the layer 2 devices, the bridge and the switch, will always forward broadcasts. A broadcast is to every MAC address, and therefore these devices that forward based on MAC address say that every MAC address includes the ones on the other part of the segment. While they would be responsible for the collision, not the transmitting node of the broadcast, but the bridge or the switch itself would be the transmitting node to the other portions of the segment. They would be responsible for the collision, therefore they are the boundary for the collision domain. But because they are forwarding the broadcast to those other adjacent pieces of the segment, they do connect these 2 broadcast domains together, and as a result it is one contiguous broadcast domain with the bridge or the switch in the middle. Now the router does not forward broadcasts. So the router is the boundary for the broadcast domain. And remember that the network interface card on the router that is attached to the segment we're describing is also part of that segment and part of that broadcast domain and that collision domain. It is just another node on that same segment, and as a result could be part of a collision or something on that segment, but does not forward those frames directly. Therefore is the boundary for both the collision domain and the broadcast domain. Now one more definition we need to look at here is the term called the socket. In the early days of networking, we didn't use the internet protocol. It was just being developed, and our networks operated based largely on MAC address and some other addressing schemes that were encoded into the network interface cards. However, as IP addressing became popular, the term of the socket also became a requirement for understanding if you're going to be working on these computer networks. So the socket is the IP address followed by a colon and then the port number of the service you're looking for on the computer with that IP address. So the IP address or the socket itself describes the major network, the subnet, that's a smaller network, the specific host computer on that major network and subnet, and even the service requested on that particular host. So this got all the way down to not only am I trying to get to that subnet and that particular host on the subnet, when I get to that host on the subnet, I'm looking for DNS name resolution, or I'm looking for a DHCP address lease, or I'm looking for server message block server, a file server in the Windows world. That port number defines the service, but the network address, the host address, and the port number collectively establish something called a socket. And if you wanted to refer to the bidirectional socket, the socket would include the source port number as well as the destination IP address and destination port number. So a fully addressed socket would include both source and destination components. Now that we've got these definitions under our belt, we've got a good foundation to move forward. We'll take a quick break here and we'll pick up where we left off. Let's continue our discussion of the network infrastructure by looking at layer 1 or physical layer devices. Devices would be hardware that are used to build this network. So layer 1, the physical layer, as you recall, has no logical filtering or intelligence capabilities. There's no decision making, there's no analysis. Basically, anything at layer 1 only understands binary bits. It hears a binary 1 in one side and it retransmits it on the other side. It doesn't understand what that bit is or means or what it's a part of, whether it's a SMTP protocol or some other protocol. It has no understanding whatsoever. It simply deals with the binary bits. So a handful of the devices that operate at layer 1 would include the network interface card, and I always call this a NIC to keep it short and sweet. So if I refer to a NIC, that's what I'm talking about, a network interface card. Now, all the nodes that are attached to your network must have a NIC, and that would include the infrastructure components like routers and switches and things along these lines. They have to have some electronics that connect them to the media that perform the modulation and encoding of the binary data bits that are the signal and the data that you're transmitting from point A to point B on a network. Now, the network interface cards attach the node to the network and also are uniquely identifiable. They use a 48 binary bit MAC address, Media Access Control address. Those 48 binary bits are typically represented in 6 pairs of hexadecimal characters. And those characters are generally separated by either a space, a colon, a dash, something along those lines. There's no real standard on what you use to divide those pairs of hexadecimal characters. So don't be surprised if you see colons versus dashes versus just spaces. The next layer 1 device down we want to talk about is called a concentrator. The concentrator was the first centralized connection point for the star topology. The concentrator was unpowered. Basically, it was simply wires connected together. There was no need to plug it into any electricity. There were no blinking lights. There was no repeater functionality. It basically was a connection box. And then each node would be connected using the proper media to the concentrator. An example of a concentrator was the token ring multi-station access unit, was commonly called a MAU or an MSAU. MSAU. And again, unpowered, no repeating capabilities. As a matter of fact, they were mildly famous for degrading your signal because of something called insertion loss. Now, the media itself, this would be your coaxial cable in a 10-base-2 network, the BNC connectors and the BNC terminators. These are part of the media. Ethernet cable, that's UTP and STP. The fiber optic cable, and even the air when we're talking about wireless communications, these components are our media and they are physical. The next one down is the repeater. Now the repeater placed the concentrator. The repeater was a concentrator, but it was powered and it regenerated the signal. So the repeater defeated attenuation. In other words, a node would transmit a frame, a series of ones and zeros. That series of ones and zeros would commute through the media to the repeater, and the repeater would regenerate those ones and zeros because the attenuated ones and zeros were difficult to understand. It would create brand new square and tall and straight and full size ones and zeros. In other words, it would regenerate the signal to a clean, fresh signal. Now, the hub that did replace the concentrator had the repeater built into it for digital signaling. Side note here, the repeater generally was referred to for digital signals, and an amplifier is generally the term used for radio frequency or analog signals. So the amplifier did the same thing the repeater did. It generated the analog signal that it heard. It would listen on one side and hear the radio frequency signal, and it would simply regenerate that signal on the other wire to regenerate it so that we could extend the data run longer. Again, the hub replaced the concentrator. It had a repeater built into it. Typically, they were digital in most cases. Then another layer 1 device is the wireless access point. That is radio frequency radios for transmit and receive, and the antenna components of the wireless access point are all physical layer devices. Now, the wireless access point also performs a bridging function, and as a result, we'll see this wireless access point also when we look at layer 2 devices next. Layer 2 devices will start with the bridge. As we've already said, the bridge memorizes MAC addresses on each of its ports. When we plug the bridge into a segment, we'll have a left-hand part of the segment and a right-hand part of the segment, for example. And the cable that plugs into the left-hand part will have multiple nodes attached to it. And what the bridge does is it memorizes the source MAC address that it hears on that left-hand port. And it builds a table of MAC addresses on that left-hand half of the segment. It'll do the same thing for all the source MAC addresses on the right hand of the segment as well. It'll build a separate MAC address table, and it will memorize all the MAC addresses that reside on the right hand half of the segment. And now, when a node on the left hand side of the segment transmits to another node, the bridge will receive that transmission, because all nodes on the segment will receive that transmission. And it'll look at the destination MAC address. And if the destination MAC address is on the left-hand part of the segment, because the source and the destination are both on the left-hand part of the segment, the bridge doesn't ever forward that transmission to the right-hand part of the segment, reducing the amount of traffic on that right-hand part. However, if the source on the left-hand part of the segment is transmitting to a MAC address that the bridge knows is on the right-hand part of the segment, the bridge would store that information, the entire frame, and then when media access methods would allow, the bridge would forward that transmission over to the right-hand half of the segment. It broke the segment in half, and the goal was to reduce the amount of traffic and nodes on each half. And it made our networks operate a little more efficiently. Now, back in the old days, these were very expensive devices. They typically only had 2 to maybe 4 ports, and it would cost thousands of dollars to buy these things. And we used them sparingly only when we needed to. Now, because a broadcast will always be a layer 2 broadcast, the MAC address for the destination of a broadcast is always going to be all Fs. That says send this frame to all MAC addresses. Well, because all MAC addresses includes those on the left-hand side and those on the right-hand side, the bridge will always forward all broadcasts to both sides of the bridge. We'll take a quick break here and we'll pick up with the networking infrastructure lecture in just a few minutes. Picking up where we left off, we're looking at the functionality of a bridge. And again, a bridge is placed within a segment to break the segment in half. It's still one complete segment. It is still one complete broadcast domain because the bridge forwards all broadcasts. It separates the segment into 2 separate collision domains. Now again, the way the bridge functions is it listens to the source MAC address on each of its ports. In this particular diagram, I have a bridge with 2 ports on the left-hand side and one on the right-hand side. So it will have 2 separate MAC address tables, one for all the source addresses it hears on the left-hand half of the segment, and one for all the source MAC addresses it hears on the right-hand half of the segment. You can see the MAC address tables shown above the bridge, one on the left and one on the right. Well, if a node on the right-hand half sends out a transmission to a destination MAC address that is on the right-hand half, the bridge will recognize that, and it will filter that and not forward that frame over to the left-hand half. So I've reduced the amount of traffic in this particular example on the left-hand half. Now, if a source on the right-hand side sends a frame to a destination MAC address that the bridge knows is on the left-hand side, then the bridge knows that it has to forward that transmission, that frame, to the left-hand half of the segment. So again, we've reduced the amount of traffic on each of the 2 halves, and this made the networks operate more efficiently when they had previously been a little overcrowded. Now, an extension of the bridge is a device called the switch. Back in the old days, that two-port bridge that we just described might have cost $2,000 or $3,000. They were quite expensive. However, as the price of the electronics came down and down and down and down and down, we found we could replace our hubs with switches that operated as a bridge on each of the ports. So now instead of having a bridge connected to a hub that connected to 24 other nodes, we have the switch that replaced both the bridge and the hub, but now each node is bridged into the network independently. The bridge still memorizes the source MAC address for each port. And in this case, it typically is a one-to-one mapping now. So most of the ports on the switch, which has now replaced the hubs on our corporate networks, most of those ports simply have to memorize one MAC address, the one node that is attached to port 27, for example. We have much greater performance and capacity, if you will, on each of our segments because of the implementation of these switches replacing the bridges. So all of the hubs, to the best of my knowledge, I haven't worked on a network for a long, long time that had any hubs left. All of the hubs have been replaced today with switches, which basically is a bridge to each and every port, and one port typically connects to one node. Now you do daisy chain these switches together. So you will have one in port and one out port as you daisy chain switches together. Those will have a very large number of MAC addresses that it has to memorize. However, typically the bulk of these ports would only have one node attached to them, and therefore it makes for a very efficient transmission. See, when the switch is communicating from, let's say, port 3 to port 27, only those two nodes recognize that the network is busy. The other devices that are attached to that same switch are unaware of the transmission because they are disconnected from the backplane at that point, the backplane in the switch, and they think the network is available. So if they are listening before talk, doing their clear channel assessment, they think the network is free and they begin transmitting. So what these devices do now is they store that transmission and wait until the backplane is free, and then they will make the connection to the right port and forward that frame to the one and only one destination port. The rest of the ports on that switch are completely unaware that a transmission ever even occurred. Now, because we've moved from layer 1, the hub, to layer 2, the switch, layer 2 now has some intelligence. It has some electronics and it has some programmatic smarts. So we can now add specialized, largely security-related applications and management to the switch. See, the hub had very basic electronics. Basically, it was a repeater. It was a connection box and a repeater. Well, the switch has filtering capabilities, so it has to have some computational capability, some CPU, and some program that applies that filtering logic. Well, if we can do that filtering and run those calculations, we can add other programs and applications, features, if you will, that provide us other benefits on our network. So what we're going to see is, since we have the switch connected to each and every port discretely, each and every node discretely now, we can add specialized filtering capabilities to these ports and begin to manage our nodes a little more efficiently, and also implement security controls to keep our network more secure. Now, another layer 2 device is the wireless access point. As we said, the wireless access point is a combination of a layer 1 device, that's its radios, the transmit and receive radios, and its antenna. Those are physical. However, because the wireless access point bridges between wireless nodes and between wireless and wired nodes, there is a bridging function, which is a layer 2 function. So the wireless access point also operates at layer 2 of the OSI model. And now a third device that operates at layer 2 of the OSI model is a modem. Now, these don't get much use anymore. These were used in the early days when dial-up over the analog telephone lines were the only way you could connect one computer to a different computer. This was before we had really a full-blown internet that people were attached to. And basically, you would need to know the telephone number for a computer that was also configured with a telephone line and a modem. Now that term modem is a combination of modulate and demodulate because our computers spoke in digital terms, ones and zeros, but we were transmitting that digital signal over an analog telephone line. So it was modulating and demodulating to communicate with a remote modem across standard analog telephone lines. Why don't we take a break there and we'll pick up with other networking infrastructure devices. Continuing our discussion of network infrastructure devices, we're looking at the switch, a layer 2 device. As we said, a layer 2 device must have some sort of CPU and must have some application program to perform the logic of filtering based on MAC address. And because we have a CPU and the ability to store and process a program and the data that's flowing through the switch, we can now add additional security type of applications as well as management type of applications to that switch. And now we have much greater control, much more granular control over the network infrastructure through applications on the switch. Now these are extra components that are added to this layer 2 device that provide additional capability and functionality. It still is at its core a switch, a layer 2 device. But we're adding increased intelligence, increased capability, increased functionality that may sound like something above and beyond a switch. Recognize it's still a layer 2 device. It's a switch, but it's been educated and elevated a little bit. It's still a layer 2 device. Now, this lecture is about the VLAN functionality, a significant improvement in security because of the popularity and the very routine implementation of the switch as the core component for attaching your nodes to the network. Now, because we have intelligence associated with each and every port on the switch, if our switch has the capability, and most of them do, many of them do, especially the enterprise grade switches, we can logically assign segment type of information. In other words, while the switch used to be the thing that held a segment together, and any node that was physically attached to the switch was part of the same segment because of its physical connection, we now can logically, through administrative controls, define that some of these nodes I want to be segregated from other nodes. So I can take a segment that was defined by the switch and bounded by a router, and I can now logically break that up so that a broadcast on one VLAN, these are called virtual LANs, that a transmission on one VLAN is never heard by a node on another VLAN, unless of course it goes through the router. So we can say that in this example we have the red VLAN and the blue VLAN. These are logical assignments that I'd go into some administrative or management console on the switch, and I would say these ports are going to be red VLAN and these other ports are going to be blue VLAN. And there are different implementations of how this actually operates. It could be done by MAC address, but typically it's done by the port number itself. We could say that ports 1, 2, 4, 5, and 6 are red VLAN, and they are going to be logically isolated from ports 3, 7, and 8. Now I've logically segregated these so that if anybody on the red VLAN, like port number 1, if that port number 1 sends out a broadcast, remember the switch transmits all broadcasts to all nodes in the switch. Now, because of the VLAN functionality, that broadcast on the red VLAN will only be transmitted to the nodes on the red VLAN and not to the nodes on the blue VLAN. So here we have segregated the red nodes from the blue nodes, at least at the broadcast level. And I can assign further restrictions between the red VLAN and the blue VLAN if I care to. And again, assuming that the software in the switch supports it. So again, it's a matter of the specific implementation by the vendors. The only way that a red VLAN node could communicate with a blue VLAN node typically is that I would use different IP subnets for the red VLAN nodes and a different IP subnet for the blue VLAN node. They would both point to the same router interface, and I'd have two IP addresses on that router interface. one that was compatible with the red VLAN and one that was compatible with the blue VLAN. And then red VLAN would send the frame to the router. The router would make a routing decision and put that frame right back on the same wire, only now it's to the destination IP address for the blue VLAN. So the routing function would have to kick in. That's a layer 3 function. And the forwarding capability would not be through the switch based on layer 2 data, but through a router based on the layer 3 data. So this is the VLAN functionality of a switch, a layer 2 device, one of the core components of your networking infrastructure. Now looking at layer 3 network devices, we get to the router. This is one of the core components of your network as well. So the switch and the router, I would say, are your two primary devices. Another device that's coming up quickly is the wireless access point. But the switch and the router are, I would say, the top two guys in your network infrastructure. Now, this guy is smarter than the switch. He understands some layer 2 information, he understands some layer 4 information, but primarily he focuses on layer 3 data, the IP address, as we typically use today. He can be configured as a firewall. That's another great feature of the router, is I can assign something called an access control list, an ACL, to the router, and I can prohibit certain types of traffic based on IP addresses and based on ports and protocols. So I can limit traffic flow filtering through the router. Now the router, as you recall, is the boundary for a broadcast domain. He does not forward any broadcasts. Each interface on the router will participate with broadcasts for the broadcast on that segment, but will not commute those broadcasts to other interfaces. So he's a boundary for the broadcast domain. He also is a boundary for the collision domain, because if he is going to forward a packet at layer 3, he will store that packet and then forward that packet on to the next segment when media access methods allow. So again, he is a boundary for both broadcast domains and collision domains. Now some routers, and typically these are done on larger scale networks, do something called cut-through that is different from the store and forward I've been describing. So there are some exceptions here, but fundamentally for your level of understanding right now, consider that the router is a store and forward type of device. It stores the information, then can process it, and then would make a decision about forwarding or not forwarding appropriately. The router has to be taught what the network architecture is like. And here we're talking about the logical address space that gets assigned to the physical subnets. So as we attach Ethernet cables to the port on a router, and the other end of that Ethernet cable connects to a switch to establish the segment, we would also assign an IP address space, or IP address specifically, to that port. Now that defines the address space for the segment. And in this way, we teach the router about the IP subnets that the router is attached to. However, very often we'll have multiple routers in our environment, and we will need to teach those different routers about the networks that can be connected to through other routers. And this is a definition of either static routing or dynamic routing, because the router will hold this table in its memory so that it can make the appropriate forwarding decisions. We have this route table that is established in the router, and we'll talk about either static assignment or dynamic assignment. And we'll talk about some protocols that are used so that the routers can teach each other dynamically about all the networks they know about. Now we're going to take a break here, and we're going to pick up with layer 3 network devices in our network infrastructure.